Hello, good people. This is section 3.6 from Calculus Early Transcendentals by James Stewart, and we are talking about derivatives, and this section is on derivatives of logarithmic functions. So let's first take a look at the function y equal to log base a of x, where a is a positive integer, and we want to derive what is our derivative. Well, this is a transcendental function, and we're going to transcend it and turn it into an exponential form, and it is equivalent to a to the y is equal to x. Okay, and this is an explicit function because y is explicitly solved for. And now this is an implicit function where y is not explicitly solved for. It's an explicit function of x, or of y, but it's not, y is not an explicit function of x in this form. And so since y is implicitly defined as a function of x, we're going to use implicit differentiation. And we want to recall that if we've got y equal to a to the x, then y prime is going to be a to the x times the ln of a. And so if we're going to use implicit differentiation here, remember that every term that contains y gets the chain rule because y is implicitly a function of x, and every x term gets normal differentiation. So if I'm going to perform differentiation to find dy dx, I'm going to differentiate both sides of the equation here, and a to the y is going to be a to the y times the ln of a, but then times dy dx, and that dy dx is the chain rule part. It's the derivative of the inside. And the derivative of x is equal to 1. And then in my next step, I solve for dy dx. And when I solve for dy dx, I'm going to divide both sides by the coefficient on dy dx, which is 1 over a to the y times ln of a. Now, if I want to put that function to be, since we started with y equal to log base a of x, we started with explicit form, then we would want dy dx to be exclusively or explicitly in terms of x. Well, I do note that I have an a to the y, but I also know that a to the y is equal to x, and so we have here dy dx is equal to 1 over x times the ln of a. And that gives us our first rule for log base a of x. So for any base, then your derivative is going to be 1 over x times the ln of a. So now let's take the look at the derivative of the natural log. Okay, and we know that y equal to ln of x is equivalent to saying it's the log base e of x. And if I take my derivative using the rule up top, then this is going to equal 1 over x times the ln of e, and we know that the ln of e equal to log base e of e is going to equal 1. So we know that if we've got the derivative, or if we've got y equal to the ln of x, the derivative is going to be 1 over x. So now, of course, we have a new differentiation rule with these two, and I thought we could go over some examples of using the chain rule with these two. All right, so here we go. F of x equal to sine of the ln of x. It's not sine x times ln of x, so I know this is a composition of functions, and so I have my outside function is sine, and if I'm going to use the chain rule, my f prime of x, the derivative of the outside is cosine. We're going to evaluate at the inside, but then we're going to take the derivative of the inside. So our function is just that. It's equal to cosine, or derivative, cosine of the ln of x over x. And we're happy about that. even if it does look a little funky, we have a formula and we can evaluate. F of x equal to ln of sine squared x, that is equivalent to ln of sine x squared. So we really have two chains, right? Our outside function being ln of x, our inside function being another chain. So we would have an ln of sine x squared, and then our inside would be sine x. Okay, so now I'm going to take the derivative, and the derivative of the outside is the ln. And what is the derivative of ln? 1 over. So I would say this is 1 over. And it's going to be evaluated at the inside. And evaluating at the inside, I get my sine x squared. But now I need to multiply by the derivative of the inside. And the derivative of the inside is itself a chain rule. And so we would be doing 2, the derivative of the outside, evaluated at the inside, but then times the derivative of the inside. And the derivative of the inside, sine x, is cosine x. And that's a double chain. I then want to clean things up, and I can cancel 1 sine x with 2 sine x's to leave me 1 sine left over. And I can also note that cosine x over sine x is going to give me a cotangent x. And so I can conclude in its simplified form that f prime of x is going to be 2 times cotangent of x. All right, so let's take a look at some other ones. This one, g of x equal to the ln of x times e to the negative 2x, is another chain rule. And I do notice that my outside function is the ln. So I know my derivative is going to be 1 over x e to the minus 2x, but then times the derivative of the inside. And the derivative of the inside is going to involve the chain rule, right? So if I have here y equal to x e to the minus 2x, I see that this is an f times a g, and so I know that my y prime is going to be the derivative of the first times the second plus the first times the derivative of the second. And I can make a little table here. If f here is equal to x, then f prime is equal to 1. And if g here is equal to e to the minus 2x, that itself is a chain rule. And I have my g prime is then going to be e to the x, but it's evaluated at the inside, but then times the derivative of the inside. So I have finally that my g prime is going to be minus 2e to the minus 2x. So now if I just take this formula here, which is the derivative of the inside, so it's a little complicated, I have my y prime equal to f prime times g plus f times g prime. I'm just going to plug in my values. The derivative of the first is 1. G is e to the minus 2x. And then plus the first f is x. And then the derivative g prime is minus 2e to the minus 2x. And if I clean that up, I end up with e to the minus 2x minus 2x, e to the minus 2x. And you could, if you wanted to, factor out the e to the minus 2x and get minus times 1 minus 2x. This is the derivative of the inside. So if I grab my original derivative using the chain rule, I have my function here and my derivative of the inside, so I finally get my g prime of x from the beginning is 1 over x e to the minus 2x, and then times e to the minus 2x times 1 minus 2x, and I quickly see that I have a common factor of e to the minus 2x, and I would get that finally my g prime of x is 1 minus 2x over x. Pretty cool, huh? So notice that sometimes if you need to, it's okay to take intermediate step and calculate something separately before plugging it back in, just to see it. All right. How about this one? Log base 2 of x times log base 5 of x. So again, remember that if we've got a y equal to log base a of x, then y prime is going to be 1 over x times the ln of a, right? So we've got 2 here as our a. So I'm first going to, and that is our outside function, the log base 2 is our outside, so we're going to say y prime is going to be 1 over times the ln of 2, because that is our base. And it's going to be evaluated at the inside. And what's the inside function? X times the log base 5 of x. And so again, I want to say times the derivative of the inside. Let's chain rule. So if I go forward and take my derivative of the inside, let's call that a g, just for the sake of making a different variable change. This is x times log base 5 of x, and we still have or let me, I guess, call it a different function, h, derivative of the inside. This is another product rule, f times g, so I know that my h prime is going to be the derivative of the first times the second, plus the first times the derivative of the second, and I can see here my f is going to be x, my f prime is going to be 1, my g here is log base 5 of x, and so my g prime is going to be 1 over x times the ln of 5, right? So now I want to plug that into my h prime, and so my h prime being the derivative of the first, which is f prime, is going to be 1, times the second, which is log base 5 of x, plus the first, which is x, and then times the derivative of the second, and the derivative of the second is 1 over x times the ln of 5. We can clean things up, we can cancel our x's, and so our h prime, which is the derivative of our inside, is just going to be log base 5 of x plus 1 over the ln of 5. So now when I go back, and that's my derivative of the inside. And so when I go back to my real derivative that I want to take, and I've placed it down here, my derivative of the inside here is going to be my y prime is going to be 1 over x log base 5 of x times the ln of 2, but now my derivative of the inside is going to be log base 5 of x plus 1 over the ln of 5. And in the interest of time, I'm not going to convert that to one fraction. I would distribute the outside into the inside two terms, and then I might take it all over the same denominator. Good. All right, so final example here, and just taking derivatives of logarithmic functions. I have f of t is equal to ln of t squared times sine of t. And I do have that this is a derivative of a product. So I know that my f prime, again, is going to be the derivative of the first times the second, plus the first times the derivative of the second, where we have that f here is equal to ln of t squared, and g here is equal to sine t. Taking f prime, I notice that I do have the chain rule, so when I take f prime, it's going to be the derivative of the outside, evaluated at the inside, but then times the derivative of the inside, which is 1 over t. And then my g prime is just the derivative of sine t, and the derivative of sine t is just cosine t. So when I put forth the product, I have, or the product rule, I have 2, the derivative of the first is 2 times the ln of t over t times the second, sine t, plus the first, ln of t squared, and then times the derivative of the second, cosine of t. And the only thing that I see here in cleaning things up is possibly factoring out the ln of t, and you could do that or leave it as is. But the ln of t times 2 sine t over t, and then we would have plus the ln of t times the cosine of t, right? And there you have it. All right, so the next time we will go over logarithmic differentiation, and that will take